Hi, so the course name is Basic Electronics, course code EC201 or EC101. Myself, Dr. Vishwarup Nyogi, Associate Professor and the Head of the Department of Electronics and Communication Engineering Department, JS College of Engineering. So, in the previous some couple of classes, we have already start this particular subject. But I'm several times recapitulate this particular subject because you have to you must know about this, and you have to you should love this subject for that reasons. So this is the prerequisite. That's the same like that the basic electronics for to know about the basic electronics, that is mandatory to know about the DC. You have the concept of the DC, direct current, alternative current, and the electricity fundamental and KCL, KVL, Ohm's law, and also the Ampere's law, all these things, Kirchhoff's law, these things. These are very important for you. And next slide, that the course outcome, that is the study of the PN junctions diode, ideal diode, diode model and its circuit analysis, applications and the diode and special diode. Learn how to operational amplifier uh, are modeled and analyzed and designed op-amp circuit of the perform the operations such as integrations, differentiations, electronic signal. Study the concept of the both positive and negative feedback of the electronic circuit, and the develop the capability to analyze the designs simple circuit containing non-linear element such as transistor using the concept of load line, operating points and incremental analysis. The things is that we are concentrated in these particular portions. We are specifically concentrated in these particular portions. Sorry. We are concentrating these particular portions specifically. Okay, so these are very important. This this diode portion specifically. So we are mainly concentrate on these particular portions is now. Okay, that is the diode portions presently. So uh, this is the COPO mapping, which is very important at present now on Washington Accord. So this is the module 1, and today we're just going to understand about these portions, okay, these particular portions. So PN junctions and FB, it is not Facebook, it is the forward bias, and RB is the reverse bias, and its related analysis we have to understand today's in this today's topic. Okay, so first of all, I don't know that I hope all of you know that this is the PN junctions. And in case of the PN junctions, if we can just go through the positive forward bias in here, and negative forward bias and reverse bias in here, then automatically current flow in this side, this is the positive side and this is the negative sides, and through that the positive terminal to the battery and P regions. So this is the forward bias conditions of the diode. And in that forward bias, if the if the voltage in the forward bias is above a specified range, the electrons in N region drifts through the junctions and migrates to the P region, and the holes in the P region drift through the junction and migrate to the N region. These things is happened, and then the current flow is going on. So this is the actual fundamental themes of the forward bias considerations. Okay, next is the this is you show there is a happening that the blue color this the holes are coming to this side and the electrons are jumping to this side. Now the current flow across the circuit As the current flow, as the current flow, so there is a there is a there is a open circuited thing, that is the switching circuit, switch on conditions at present now. So at that time the current is flow, that is the PN junction, simply PN junctions forward bias. Okay, so now what happened about the reverse bias? The that means the I'm just changing the bias conditions, that is positive and the negative, in the negative side in this side and positive in this side. And for that reasons what happened, for that reasons what happened, the current the battery is connected with the negative terminal to the N region and positive terminal to the P region. Then for that reasons the depletion regions white is increasing, the depletion regions white is increasing. And for a very small amount, the minor amount of the current, for the purpose of the minority carrier, the current will flow, very minor amount of the current for the purpose of the minority carrier. Suppose in here the minority carrier is electron, and suppose in here the minority carrier is a hole. Okay, that is N type and P type. So for that reasons is very small current is flown, the holes get attracted to the negative terminal of the battery, and and uh, and electrons get attracted to the positive terminal. You show the holes are holes are attracted this side, holes are attracted in this side, this side, this side, and electrons are attracted in this side. Okay, because this is the positive terminal and this is the negative terminal. So for that reasons, you show in the next second, you show there is a electrons are attracted in this side and holes are attracted in this side. So as the holes and electrons are attracted, this result in the increase of the depletion regions, and for that reasons you show the depletion region which is increasing, that is the depletion regions. In the previous case it's we did this, and at present now the depletion regions will become high. I think you know about this depletion regions, we have covered this depletion regions concept in the previous video, we have covered it in the previous video. Now today we just understand that why this depletion regions increasing, because of holes are attracted in this side, and this side is the electrons are attracted, and that's why it's white, become white. Okay, and as a result these things is happen. And now the PN junctions, PN junctions act as an insulator, will now allow any current, will not allow any current to flow in this current, in this circuit. There is no current flow, but a very nominal amount of current can be flow for the purpose of the minority carrier, for the purpose of the minority carrier. If there is some sort of electron and if there is some sort of hole, so for that reasons only a very small amount of current can be flow, but majorly the current will not flow in this particular regions. Okay, so so if the battery voltage is above of the particular limit, reverse bias, if the actually what happened, what is the meaning of the bias? Bias means, suppose there is a mobile, I want to bias it from, suppose this mobile in this positions, I want to bias this mobile from this positions to this side. I'm just apply one force and it's moved from this side to this side. Okay, so that is actually the bias. Okay, that means I'm applying the voltage with some directive play, that is called a bias. And in case of this electronics, in case of this electronics, we have also applied the voltage. This is actually nothing but a force. This is the force means electromagnetic force. The force means it is electromagnetic force. I hope you can understand, that is EMF. This EMF we are applying, this particular EMF is electromagnetic force, and this is also a voltage. Okay, so if this voltage is much higher, if the battery voltage is above the particular limit, above this particular limit, then what happened, the reverse bias breakdown voltage the reverse bias breakdown voltage greater than the reverse bias breakdown voltage. If there is a reverse bias breakdown voltage, if it's enhanced, then automatically the bonds will destroy and a huge current flow. Bond will destroy and a huge current flow. Basically, what are the statements I am explaining at present now? What are the statements I am representing right now? That is actually hypothetically represented by Avalanche, Professor Avalanche. And that's theory, that's concept is called the Avalanche breakdown concept. So what I'm saying? I'm saying that this is a reverse bias potential. In this reverse bias conditions, if I'm increase the EMF, if I'm increase the reverse bias voltage highly, if I'm increase high and high and high, after a certain age, this barrier is destroyed and all the bonds are destroyed and a huge current flow, that is the reverse bias. You show there is a electron and holes break down through the PN junction and cross result in the current flow through the current. You show a huge current flow, blue and green color. This show this a huge current flow at presence now when the bond is breaking. So that is actually the representing by the avalanche, and that things is called electron and holes break down through the PN junction and cross the result in the current flow through the circuit. That is the breakdown concept. And a huge current flow, that is called the breakdown. And these particular things, this particular breakdowns is called the avalanche breakdown, as avalanche, Professor Avalanche is representing these things, that these things is happened like that way. That is called the avalanche breakdown concept. Now, in this process, the current flow through the PN junctions is very high and unlimited. Ultimately, the PN junction gets damaged due to overheating caused by the excess flow of the current. It's a very important term, important representations. The things is that whenever I am increasing this voltage and increasing this voltage, after certain time the voltage is very high, bond are all break and huge current flow. But it is hypothetically perfect, the avalanche breakdown. These particular things hypothetically perfect, but for the realistic matter, for the purpose of the realistic matter, it is quite difficult, because if I want to reach this particular voltage at that time, what happened? A At that time, what happened? It cannot be possible to at that time. What happened? The diode will destroy, because it cannot be able to take resist of that much voltage. The diode will destroy. So that's why I'm written that in this process the current flow through the PN junctions is very high, and ultimately the PN junction gets damaged due to the overheating. There is a huge heat will be generated, and for that the heat generations caused by the excess flow of the current, and for that reason the diode will be damaged. Actually, whatever, the diode will burn. Actually, diode will burn. So we will try this experiment in our lab also, that I'm increasing voltage for the ordinary diode. Then what happened? So you can also try it. A very small amount of diodes is a very costly, is very small. So we can able to do these things, that in the reverse bias, if I increase the voltage, then what happens? Actually, here I am representing the some mathematical aspect. That is actually the symbol of the diode. That is actually the symbol of the diode, and that is the representations of metallurgical junctions. And this side is the anode, and this side is the cathode. A diode is formed by the joining of p-type and semiconductor with p-type semiconductor, and n-type junction is interface between p and n. And here you show that is p number is representing Na, and n number is representing Nd, and Np is representing Ni square by A. Pn is representing the strain, that is representing P, that is the representing Np, that is Ni square by Na. So this is a representations of amount of charge and amount of P and amount of in strength in here. You show here the PN junctions electrostatics representations, which is there is a depletion region, and that is spread in here, and natural regions is this side and this side. This is the depletion region, and there is it is representing that the value of pp and value of np, value of pp and value of np, very easily value of pp and value of np and value of nn and value of np, which is basically 10 to the power 7 by centimeter cube. It is also 10 to the power 3 by centimeter cube, and here also 10 to the power 16 by centimeter cube, 10 to the power 4 centimeter cube. So like that way the Johnson electrostats statics represent, that is also the electric field, how it is spread, how it is representing that things also. That is the Carl E and rho C gamma and XC, that is like that way we are representing in here. And this K is basically the Boltzmann's constant, T is the absolute temperature, and like that way we can representing the potential across the PN junction. This is the representations of potential of the charge density, electric field and potential. Actually in your syllabus you just know about these expressions. This expressions is very much mandatory. That derivations is not in your syllabus as per the syllabus we have already discussed. So you go for this the depletion with how we can, and this is the representations again, the with depletions regions, how we can represent the depletion regions with, that is wd is the xn plus xp, which is this previous case we have already seen, and in this added this 2 and representing this. So this is a very important equations, this is very important equations for you. Okay, so basically one problem is there to fill the built-in potential. What is the problem? Find the built-in potential and depletion region with for a given diode, given data on n type site is the na equals to n type site, na is representing here in type in inside na is representing here this, and nd is the is the it is the p side, sorry, p side, and it is the n side, nd is that, it is the na is the acceptor and is the donor. So the absolute room temperature, that Vt equals to this. So analyze, basically we know about we know these particular equations, we know these particular equations, we just put all these value Vt, Nd, Nd, Ni square, all these value we just put in here, and just after putting we get these particular things. Mind it, or Ni square is representing 10 to the power 20, 10 to the power 20, because you saw this is the maximum value nd, so that's why we are just representing it is the 10 to the power 20. We are considering the maximum value always. So if it is 10 to the power 23, or if it is the 10 to the power, it is greater than value of this, then we can consider this, and like that we just put this value and get the determining these things. Okay, and then after then wd we can calculate by using this particular equations, and these equations is also very important, and we put this all this value and determine that is equals to this. So that is 0.11 0.113 micrometer. So these things is representing in here. Next uh, next we go for this diode equations, which is, so how this diode equations coming and all these things, I will come to this matter and I will explaining the previous explanations in the next video. But things is that first we have to know about the expressions of the diode equations. This, in this case of diode equations, this is is the reverse saturation current. vd is the voltage applied to the diode. vd is the voltage applied to the diode. Q is the electronic charge, 1.60 into 10 to the power minus 19 C. Okay, K is the Boltzmann's constant, and that is also have the value. T is the absolute temperature in the kelvins, and the N is the non-ideally factored, and this is Vt equals to Kt by Q, thermal voltage, and these things is also in room temperature we can consider it as a 20 mV at room temperature. So this is the equations, diode equations, which is very very important, and how the equations is formed and all those things we can go for that. uh, First of all, we just go for the diode characteristics and then we can understand about these diode equations and all those. Uh, Before that, I'm just elaborating very, very simply, we just representing in here that uh, that is the actually diode forward bias diode voltage curve, and that is also the diode voltage curve, and you show the equations of these which is looks like which can support this particular equation, this particular graph. This is the actually diode forward bias path. Okay, so I can understand, dear students, that VI characteristics of the diode is not too much complicated like that which we are representing in here, but you can understand very easily. Just wait for some time, sometimes. Okay, this is the external reverse bias added to build the potential of the PN junctions. The shaded region below illustrates the increase the characteristics of the phase charge and region due to the externally applied reverse bias reading. Okay, that is the field representations which we have already representing in the previous things. So this is the depletions width of the increase and reverse bias voltage. Reverse bias voltage, how increasing that things are representing in these particular expressions. Actually, in your syllabus only expressions is written. So for that reasons I am representing like that way. Okay. So this is the junctions capacitance. How the junctions capacitance we can representing the charge in the voltage lead, the charge in the voltage lead in the charges of depletions width of the charge. This lead is capacitance that we can calculate it from the charge voltage dependency. So how we can Qn equals to n QND xna nq na nd na Na plus Nd WdA and coulombs. So Cj equals to dq and dvr, that is equals to q and that is Cj not A by root over 1 Vr by phi j. So this is the representations of this particular junction capacitance, which is very very important for you. The expressions of the junction capacitance. So that's all for this particular classes. Actually, I'm not covering this lecture, I'm not covering the expressions details, and also I'm not covering the I have not covered the portions of the how the diode forward bias is working and all those things. This will we can continue in the next lectures. So thank you very much, thank you for watching.